discussions on qualitative analysis of acidity or acid strength. And this is a continuation from our first video where we actually talked about atom or element effect. Okay, so we've already talked about element, atom effects, how the element or the atom effect could affect the stability of a conjugate base. The second factor which is crucial in determining the stability of a conjugate base and thus determining the acidity of an acid or the relative acidity, the relative strength of an acid is resonance. So how would resonance explain this? So let's choose some examples to go through this. And what I have here are ethanol. Okay, we can compare ethanol to acetic acid. So if you look at ethanol versus acetic acid, these are acids. And again, like I mentioned in the first video, when we are thinking about, or when we want to think about acid strength, the structure of the acid itself does not give us any information. That is not our starting point. Okay? That is not what we think about. What we have to do is we have to think about the conjugate base. And in fact, before we go there, I'm going to give you rough approximate pKa values for these acids. If these molecules were to behave as acids, what would be the pKa values? So for this alcohol, okay, this is an alcohol, the pKa is roughly around 16. And in fact, most alcohols, they have pKa's around 16 or so, like within a range there. But we will see some variation in the next effect that we are going to discuss, okay? So that could change drastically, but simple alcohols, they would have pKa's around 16. And this carboxylic acid, it has a pKa around 4.7 roughly, okay? So those are the approximate numbers. And so when we look at these numbers, what we see is that acetic acid, it has a lower pKa. And what that means is this must be the stronger acid between these two. Now, what we're going to do is we're going to look at the conjugate bases and basically try to understand, can the stability of the conjugate base explain this observed acidity? The fact that the carboxylic acid is stronger than an alcohol that is comparable to it. Okay, or in general, like carboxylic acids being more stable than alcohols. So the conjugate base for this alcohol, remember conjugate base, what you have to do is you have to remove the proton from the acid. Whatever you get after that is your conjugate base. So I have this structure here, and as you can notice that it is very likely that the proton that is going to be lost is this proton, the hydrogen that's connected to the oxygen, because oxygen is an electronegative element. So we can write the conjugate base as that. Okay, we do not have to necessarily show lone pairs at this point. Like I said, it is, even if I just show a negative charge, it would be implied that this oxygen has 3 lone pairs around it. Okay, that would be implied in there. Okay, conjugate base for the carboxylic acid here. Again, remove that proton and put down whatever we are going to get. So oxygen with the negative charge over there. So these are the 2 conjugate bases of these acids, or the corresponding conjugate bases for these acids that are given. Okay, now to again set the stage, reiterate, okay, this acid here, which is a carboxylic acid, this molecule here, which is a carboxylic acid, is a stronger acid, and the fact that it is a stronger acid should mean that its conjugate base is more stable, okay, compared to this other conjugate base that we're comparing it to, okay, or the conjugate base of the acid that we're comparing it to. Okay? This has to be more stable. So now, when you compare the 2 structures, what you can see is for this first conjugate base, which is an alkoxide, in general, or ethoxide. So this molecule is ethanol. This would be an ethoxide ion. Okay. For this ethoxide ion, the negative charge is on the oxygen atom. Now, that may seem like a good situation because oxygen is an electronegative element. So based on atom or element effects, it should be able to stabilize that negative charge. Well, okay. Going to the second conjugate base, this conjugate base is called an acetate ion. And we know this is acetic acid. We've seen this molecule a couple of times already. Okay, so that's the acetate ion. So when you compare the ethoxide to the acetate, or the acetate to the ethoxide, what you notice in the acetate ion, the negative charge is again on an oxygen atom. So that is also a good situation, okay, because oxygen is an electronegative element, so it should be able to stabilize that negative charge. But now if you think about it, the acetate ion here, notice how this negative charge is at an allylic position to a double bond, okay? And what that means is we can do some resonance here. I can take that negative charge, push it over to that oxygen, and then move the pi bond over to the other oxygen. And what that means is we can write a resonance form where the negative charge is now on the other oxygen atom. And what that means is we've been able to delocalize, right? This is resonance. So we could delocalize the negative charge, which means it is going to make this stable or more stable compared to the ethoxide ion, where the negative charge is always localized on one of the oxygen, on a single oxygen atom, whereas in the acetate ion, because of resonance, we can spread the negative charge over two oxygen atoms. I mean, we know how to draw resonance hybrids and everything, so we can do that, and that would explain the stability. So the fact that acetate, this conjugate base, is more stable than the ethoxide because of resonance, okay? This is resonance here. Because of resonance in its conjugate base, that would explain why acetic acid is a stronger acid compared to ethanol, because its conjugate base is more stable compared to the other conjugate base. So this is less stable because there is no resonance, okay? There is no resonance, and therefore it is less stable. So we can use resonance to explain the stability of conjugate bases, right? So resonance to explain the relative stability of conjugate bases, okay? And we can then understand or explain acidity based on that. Let's look at another example, which would be on resonance again, and maybe we'll compare two structures which can both do resonance, okay? So let's think about two acids. Let's say we have double bond OH versus double bond OH. Let's say we're comparing these two acids now. I'm actually let me keep it simple for the time being. Maybe we'll look at a different example first. Okay, let's compare that carboxylic acid to a sulfonic acid. Let's do a sulfonic acid versus a carboxylic acid. Okay, this is a sulfonic acid. This is what I'm going to do here is I'm not going to give, or I will not be providing the pKa values, but we will just try to see if we can use resonance to determine which one of these two carboxylic acids is more acidic. Okay, so that is the question we are trying to answer here. Which is more acidic? Okay, sulfonic versus the carboxylic acid. So again, it really doesn't help or make sense to look at the carboxylic acid itself. So what we're going to do is, these are the acids. We're going to draw their conjugate base. I'm going to draw the conjugate base of the sulfonic acid. So there's a CH3 group here, there's an OH. Most likely that's the proton that's going to get deprotonated. So the conjugate base for this molecule should look like that. Okay, O minus on that oxygen, versus the carboxylic acid is going to look like that. Okay, now, so we have two conjugate bases for these two molecules. Now, whichever one of these two is more stable, the corresponding acid would be the stronger acid. That is how the logic would work here. Okay, so if you look at it for the carboxylic acid, we can draw a resonance form. Okay, so we can draw a resonance form for the carboxylic acid. So, and notice how these are the only two resonance forms that we can draw here. For the sulfonic acid, we can again draw a resonance form. Okay, but is that it? Can we draw more resonance forms? The answer is yes, because we have another double bonded oxygen. So we can take that negative charge and push that over, use the other oxygen. So we get a third resonance form here. Okay, so there's going to be a total of 3 resonance forms. So both conjugate bases, when we started out, the negative charge was on an oxygen atom in both cases. The carboxylate here, the acetate ion, it could do resonance and spread out the negative charge to the other oxygen atom. So over 2 oxygen atoms compared between the two structures. But for this sulfonate ion, the negative charge could be spread out to the other 2 oxygen atoms. We have more resonance forms here. So since we have more resonance forms, okay, this CD is more stable compared to that carboxylate. And what that means is, if the conjugate base of this acid is more stable, what that means is this is our stronger acid based on the stability of the conjugate base. So that is how we use resonance to explain the acidity, or acid strength. Okay. Let's look at a third example here, the one that I had drawn previously. So we could use the number of resonance forms to explain acidity. Let's look at the other the acid set that I had drawn. We have this acid here versus, again, a carboxylic acid. I think I've kept the carboxylic acid pretty much constant between all 3. So again, the question is, which one of these is a stronger acid? So the answer again has to be in the stability of the conjugate base. So do not talk about any explanation without drawing the conjugate base itself. The first step has to be draw the conjugate base. Okay, so you draw the conjugate base here. So minus, that is the conjugate base, versus that. So if you look at it, there is a negative charge on the oxygen atom in each case. Okay. Now, this conjugate base can do resonance. And other conjugate, the conjugate base here. This can also do resonance. Okay, so that means they both have one or two resonance forms each. Okay, they both have two resonance forms. So does that mean that these acids are of equal strength? They have the same acidity? Or is there anything else that we can identify here? So if you look at it carefully, in the first resonance form, for both conjugate bases, the negative charge was on the oxygen atom, the same electronegativity. We could do resonance on both conjugate bases, and then we got to the next resonance form, where the negative charge is on a carbon in one case and is on an oxygen in the other case. So is there a difference in stability between these two resonance forms? The answer should be yes. Okay, so now we were using resonance forms, okay, but now we can bring in atom effect or element effect. So based on atom effect, this resonance form is less stable than the other molecule, okay, because here the negative charge is on a carbon, whereas in this resonance form, the negative charge is on an oxygen. And since oxygen is more electronegative, okay, oxygen, which is more electronegative, and that means it can stabilize that negative charge better. And so what that would mean is this conjugate base overall is more stable. Okay, so in this particular example, resonance did not help us differentiate the stability of these conjugate bases. It is the atom effect. Although there is resonance possible, it is the atom or the element effect that helps us differentiate the stability of the two conjugate bases. And overall, based on all of this, we can say that this is a stronger acid. Okay, so relatively, that acid is stronger. So hopefully, with these examples, you could see, how we can use resonance in different forms to explain the stability of conjugate bases, and sometimes coupled resonance with another effect to explain the stability of the conjugate base. Okay, so that is how resonance is a factor in determining the stability of a conjugate base. In the subsequent videos, we will look at other factors that are helpful in defining the stability of a conjugate base. Bye.